Okay, so this will be a short module on the lecture that we missed this semester, which is sequential logic circuits. So I'm not going to go too much into the motivation for memory circuits. You are going to see a lot of that motivation when someone from Micron comes in and speaks with you in a future lecture in this course. But I'll touch upon memory circuits, and we'll go over the difference between combinational versus sequential circuits, where combinational is what you have seen to date. And then I want to describe the latching functionality for you in the simplest form, which is using a coupled inverter. And then we'll go into an SR latch and then a D latch, which is derived from an SR latch. So you can see the SR latch, the last schematic that we will look at is actually the latest form of the SR latch, which is memory. Okay, so main motivation is basically memory and computer system. So we have main memory, and we have which is rapidly accessible, and then we have that can be in two different forms, static memory and dynamic memory, and both of those use what we call sequential logic circuits, which have memory. So you will see something like this again from some of the companies that come in to speak with you this semester, but basically we have a bunch of sequential logic circuits, which we call storage cells, in a big array, and this would consume the majority of your silicon area. And then we have some peripheral circuits, which would be sense amplifiers and drivers, decoders, buffering would be the drivers that might interface to the outside world, where the majority of the space, again on the silicon, is taken by these digital logic circuits, which are sequential logic circuits, which are how we maintain or store our memory in the system. So to date you have seen combinational logic circuits. So those are your NANDs, NORs, NOTs, inverters, the basic things that we've talked about to date. And these combinational logic circuits do not have memory. So what that means is the output is dependent on the present state of the inputs. So the inputs change, the outputs change. The difference between sequential logic circuits and combinational logic is that sequential logic can store a state, meaning the outputs could either be dependent on the present state of the inputs, or they can hold their past state, so they can remember, which is the form of memory. Now, in essence, sequential logic is actually made out of combinational logic circuits, and what we do is we will tie the combinational logic circuit in a feedback loop, so the outputs will somehow be fed back to the inputs, and that function, that tie back or that architecture will allow for memory. Now historically this was done without a clock, so we can actually implement memory without clock, but as you will see in this module, these memory circuits have evolved to be clocked systems. Okay, so when we do this tie back, we actually get something called a latching functionality. And so I want to describe to you a latching functionality using the simplest system, which is two coupled inverters, or inverters where the output of one is tied back to the input of the other. So if you look at the diagram to the top right, we'll look at latching functionality in this manner, because sequential logic circuits have latching functionality because the output will be tied back to the inputs in some manner. Okay, so what you see on the bottom left is a butterfly, what we call a butterfly curve. The butterfly curve is actually the voltage transfer curves of both inverter 2 and inverter 1, plotted in an interesting way. So you can probably see this blue line here is a voltage transfer curve that we're very familiar with, which is the voltage transfer curve of inverter 2 here, where you have output on the y-axis and input to this inverter 2 on the x-axis. Now, the input to inverter 2 is the output of inverter 1, and the output of inverter 2 is the input to inverter 1. So if you look at the red curve, this is actually flipped on the x and y axis to also be a voltage transfer curve. So you can see here, this is actually now low values of Vn2in going to high value of Vn2in, which should give us an output low, right? So you can see this right here is the voltage transfer curve flipped about the x and y axis. And together it makes what we call a butterfly curve. Now in this system, we have just very similar to a single inverter. We have stable states, so the two stable points, right? So for very high, very low, we are in stable states. We know what we are going to latch to at our output. If we're in the middle region where we have our steep curves, this is called the metastable point. And just like when we look at a single inverter, we don't want to operate in this area. This is the unknown region. It's a steep slope. We may get the 0, we may get the 1, we're not sure. So we try to stay out of the metastable point. Now, what's nice about a latching functionality is its immunity to noise. And we can illustrate this by by starting in a stable point and then saying, okay, if we add noise to that stable point, what happens to this system? So starting at point 1 diagram on this diagram, let's assume that Vn1, which is the input to inverter 2, output to inverter 1, is a stable value of 0. And now we add noise to our system, and we know our systems have noise because we're in an environment that has noise. So we move, our noise may randomly move, right? And let's say it moves us up in voltage value Vn1. And so we start to climb closer to the metastable point due to noise. But what happens? If you look at step 2, so that noise has shifted us in Vn1. And if you look at the inverter 2's voltage transfer curve, that puts us at the output value, the purple line, output value. Now, that purple actually feeds into inverter 2. So it's point 3. It's the input to inverter 2, which actually brings us back down. If you look on the Vn1 axis, it's starting to bring us back down, the N1 point. And then moving to point 4, Vn1 is the input to inverter 2. So we go back to the blue voltage transfer curve. You have to follow that curve. And that brings us to the new purple point, which is the output to N2, which is the input to inverter 1. And then you can see, if you follow the red curve, putting an input to N2 into inverter 1, and we get the output to inverter 1 back to the stable value of 0 at 0.5. So this illustrates how we have noise immunity. We can also illustrate the ability to move away from the metastable point with the latching functionality, which is another nice feature of this coupled logic, or this latched logic. So here, now we're sitting at a metastable point. And what happens? Well, we always have noise in systems, we know that. So if we're perfectly at the metastable point for one instance of time, and we add a little bit of noise, and the noise could be in the low direction or the high direction. In this case, we're illustrating with the low direction. So we add a little bit of noise, and Vn1 starts to move down a tiny bit. Now we go to point 2. So Vn1 is the input to inverter 2. So look at the blue voltage transfer curve, and we get the purple, the new solid purple circle, right, which is the output to inverter 2. Well, that output to inverter 2 at point 3 is the input to inverter 1. So follow the red voltage transfer curve, and we're starting to come down in value for Vn1, as you can see. Vn1 in point 4 now supplies the inverter 2, which again brings us to the next solid purple circle, which is the output to inverter 2, and then again bringing us all the way to a stable value of 0. So from a metastable point, we are able to move to a stable point. So the latching functionality forces us to move back to a stable point, which is another nice feature of the latch. So we will have latching functionality in the circuits that we continue to talk about in this module. And the most common type of latch that we use in memory circuits is called an SR latch. So the SR latch comes from the name set or reset. So set meaning if your set value S is a 1, you would have your output Q be 1. Whereas reset means that if your reset value R is 1, your output would go to 0. You would reset it to 0. So this is the description of an SR latch. Now, looking at the truth table of an SR latch. So it has historically started with 2 cross-coupled NOR gates. We can actually do that with 2 NAND gates. I will let you prove that on your own, and I will give you that derivation and hand analysis in your notes, in your PDF notes. So for this case, the cross-coupled NOR gates, let's start with the 0, 1 and the 1, 0 function. So reset R is 0 and set is 1, S is 1. So because it's a NOR function, when the S is 1, automatically this NOR function will give you a 0 at its output. It doesn't matter what the other input is, because we have 1 at one of the inputs and it's a NOR. We are going to get Q bar as 0, and that means Q should be 1. Or you can look at it as Q bar feeds back 0 to G1, and R for this case, I'm losing my cursor, and R for this case, when set as 1, R here is 0, so we have 0 and 0 going into G1, so Q is 1, which comes to this point right here. On the flip side, if R is 1 and S is 0, the Q automatically goes to 0, 0 feeds back to G2, S is 0, and we get Q bar as 1. So Q and Q bar should always be opposite to each other, hence the terminology. Now let's look at the 0, 0 state. So this state is going to give us memory. So here, R is 0 and S is 0. So what that means is the outputs of G1 and G2 are dependent on the prior input value. So if R is 0, G1's output Q will be based upon whatever Q bar is. So if Q bar was 0, then Q will be 1. If Q bar was 1, Q will be 0, and it holds its last state. So then Q, same thing goes for G2. So Q and Q bar maintain the previous state or hold their value as they were in the previous state. So putting a 0, 0 into set and reset means the Q and Q bar are the same, the present state is the same as the prior state. So this is our form of memory. The 1, 1 state for the system is not used, because if you put R and S both as 1, G1 and G2's output should both be 0, and that would violate the Q bar logic. So we do not use the 1, 1 state for this system. Okay, so I'm going to let you derive both, but number 2, the CMOS logic gate implementation. So we can draw this using circuits, and I'm just going to show you the final result. Mine's very messy. So here we've got VDD. This is using CMOS logic. We have 2 NOR gates. So here's one NOR gate, here's the other NOR gate. And when we put our transistors and NMOS transistors in parallel, we put our PMOS transistors in series by the principle of duality. I have S tying as an input to one of the NOR gates, R tying as an input to another NOR gate, and then we've got Q feeding the input to the right-hand gate, Q bar feeding the input to the left-hand gate. And you can see this gets somewhat messy. We've got a lot of crossovers here. In our silicon implementation, that really would mean that we would have to do crossovers, meaning we need multiple layers of metal. And we've got 1, 2, 3, 4, we've got 8 transistors for this system. So our circuits have actually evolved. And we usually have clocked systems anyways, because we synchronize with clocks. We worry about timing with clocks. So if you have a clock in your system, SR latches have evolved to be clocked latches. And so this right here, the bottom left diagram shows a clocked SR latch implementation. So here you can see that the NOR gates are cross-coupled, just like we had in the prior slides. But we add 2 AND gates, and we clock. E is actually phase. They mean the same thing. So we clock here using the phase, or E, we clock the 2 AND gates with the R and the S inputs. So doing this clocking function actually simplifies the circuits. It is not trivial and obvious that happens, because you think, well, I'm adding 2 more AND gates. How can this be simpler than the prior slide? You won't know that until we actually look at the evolution of the clocked SR latch, and the final schematic that has come out of that, you will see becomes simpler. Again, this is not a trivial point that this is a simpler implementation. By block diagram, it doesn't look simpler. Okay, so when the clock is low, 0, these 2 AND gates are both 1s, and we have no action required, no action from the cross-coupled NORs. So we say we keep the same state. Everything Q and Q bar just stay the same. This basically, the system is inactive. When the clock goes high, then the values at the output of the 2 AND gates depends on R and S, and it actually follows the exact same truth table that was the non-clocked SR latch. So if you look on the right hand side, this truth table is the same. So when the clock is high, the truth table is the same truth table that we had 2 slides ago. All right? Okay, so let's look at this clocked SR latch implementation. This system is actually one of the first implementations of the clocked SR latch. And you can see that it doesn't follow what we typically consider CMOS logic gates. If there is no equivalent pull-up network for the pull-down network. So in this case, I'm going to do it for one side. S with the phase or clock, this is the AND function. It's actually the NAND function. So we have S in series with the phase NMOS, and so this will create the ANDing function. And then Q1 will be the ORed function with the input of this, which is actually tied here. If you look right here, Q, follow Q. Q is actually the input to Q1. The signal Q is the input to transistor Q1. So this creates S and phase, ORed with Q1, and because it's a pull-down network, all NMOS, there's a NOT there. So this is the NOR. This equivalent here is sort of done on the right side, but now it would be an R and phase ORed with Q bar, because Q bar is coming into this one. Now, the pull-up network, again, is not a CMOS logic gate pull-up network for this case. What has been done is actually an inverter has been combined with this system, and just from the inverter, so if you look, this is an input, this is an inverter, this is an output. So if you call this Q bar, this point here in the middle, then the output would be Q, and vice versa. If Q goes in, this is Q bar. So this has been simplified from a standard CMOS logic gate implementation. Mostly NMOS devices, only 2 PMOS needed, and they've done this by using cross-coupled inverters with extra circuitry on the side. Again, not trivial and not your standard CMOS logic gate. This has been done by designers over time in order to simplify or reduce the physical area of the circuit. Okay, so then what happened? Well, this is still too many transistors if you're going to do these in the billions of memory cells. So again, over time, it has been further simplified. So now we still have our 2 inverters. So you can see Q bar supplies one inverter, output Q supplies the left-hand side inverter, which then of course gives you Q bar. So this is the coupled inverters. But now the AND function has been created with a pass transistor NMOS logic, right? So this is just pass transistor logic, NMOS only, where we're going to have an R and phase here, or on this side, S and phase. So this is creating the same logic function as on the top right block diagram here, but now we have pass transistors, so we can simplify this down to 6 transistors. And this right here is the fundamental building block for the CMOS SRAM memory cell. So you can, I shouldn't say most often, sometimes Q5 and Q6 can be pass transistor logic, but it really depends on the system. And what you'll find nowadays is actually this isn't done with NMOS only because of the physical size constraint. So these tend to be NMOS only. And I think when you see some of the system level implementations that Micron will talk to you about, you will see that these are NMOS only pass transistors. Okay, so again, the circuits have evolved. The clocked SR latch has evolved over time to become this. Many designers, a lot of time, a lot of money to get a system like this. This is not trivial. This is not obvious, and it really doesn't. You might be able to see pieces of the different types of logic that we have used in this course, for instance, CMOS logic inverter and pass transistor logic, but putting them together, again, is something that has been historically done. So over time it has evolved to this clocked SR latch. Okay, so from the SR latch came the D latch. So the D latch is actually taking the S and the R inputs, creating them with an inverter in between the two. So if you looked at the system, you could say that if this was R, one side would get S and R and S, basically always opposite each other from the truth table, but we only need one input, which is data. So data comes in, it goes through an inverter to create two inputs to the different AND gates. It's still clocked, it still gets a clock E or phase, whatever you want to call it. And then looking at the 2 ANDs and the cross-coupled NORs, this just looks like an SR latch on the right-hand side. So a data latch is a derivation of an SR latch with an inverter that creates the S and the R inputs. Okay, so now we just have, again, phase and D. We only have two inputs. When the phase or the clock is low, it doesn't matter what D is. Everything stays in the prior state, just like in the SR latch. So we get Q previous and Q bar. This should be Q bar of the previous state. No change. When the clock goes high, then it depends on the data's input. If the data input is 0, then we go to a reset state. Q is 0, Q bar is 1. And when the data is 1, we go to what we call the set state, where Q is 1 and Q bar is 0. The timing diagrams are shown to the top right. You will do a few of these types of logics in your homework 3. If you look at a D-latch implementation using pass transistor logic, again with the main motivation to reduce the number of devices and use mostly NMOS, we can implement a D-latch with pass transistors, phase and phase bar, and then 2 inverters. So in this system, if you have D coming in and the phase is high, then the series switch closes and the switch in the feedback loop opens because that's controlled by phase bar. And you get D that passes to G1, that's just an inverter, to create Q bar. So Q bar is just the opposite of D. And then it passes through another inverter to get Q. So that means Q follows D, right? It's tracking D, that's why it's a data latch, when the phase is high. When the clock is low, or the phase is low, the feedback loop will close. This transistor will turn on, and this will look like a closed switch. The transistor that's in the series pass hooked to the data is an open circuit, so this switch will open, and basically Q will just feed back to the input and go through this loop. So you'll get Q feeding back to G1, which gives you Q bar, which gives you Q. So this is the hold state. So when the clock is low, Q and Q bar maintain their previous states. So this is implementing the same truth table using pass transistor logic. Now, D flip-flops are again implemented with D latches. So the point of a D flip-flop is actually to latch data or to track data at the output, Q, based on rising or falling, in this case rising, edges of data. So what happens is, if you're not rising on a rising edge of data, nothing happens to the output. It just stays at the previous state, Q. But on a rising edge, when the data goes 0, when the clock is on a rising edge and the data goes 0, the output goes 0. On the rising edge of the clock, when the data is 1, the output's 1. So it depends on the rising edge of the clock. Non-rising edge, nothing happens to the output. The output stays in its previous state. So this is very good for, we use these D flip-flops for synchronization, logic, timing, counters, where we need to count rising edges of clock signals. And again, you could implement this sort of logic with falling edges too, and then we have dual edge, rising and falling edges. So we get more complicated than the simple D flip-flop. D flip-flops are implemented with 2 D latches, basically cascading D latches in the manner shown in figure A here. So here you have a clock signal coming in. This is your phase signal, and you have D data going in, and it goes through the first D latch, and the output of the first D latch feeds into the second D latch. And then your clock signals, one's the inverted of the other, to create the rising edges. So if you look at G2 and G1 clocks, what will happen is, if you look at the output signal here, Q will only be tracking the data on the rising edge of the clock. So clock is G2, and if you look here in the top waveform, when it rises, that the data is high, D is high, so you can see the output with just some small delay goes high, Q goes high. And when the falling edge of the clock happens, or when the clock is in steady state, it doesn't matter, the output stays the same, high, and on the next rising edge of the clock, G2, again, it looks at what the data coming in D is. D is low, so the output with just some small delay goes low. Q goes low. So this is, again, dependent on the rising edges of the clock. It latches data on the rising edges of the clock, as shown in the truth table. Okay, so the master-slave D flip-flop implementation, again, using pass transistors or in a feedback loop. We have the left-hand side, you can see that was just a D latch that we had some slides ago, and you cascade 2 D latches to get a D flip-flop. Now, if you notice, this actually has 2 phases, phase 1 and phase 2. We don't call, when we implement in a D flip-flop architecture, we don't call it phase 1 and phase 1 bar or phase 2 and phase 2 bar, because we actually have to create non-overlapping clocks. And what non-overlapping clocks ensures, if you look here at the diagram, the conceptual diagram, phase 1 actually goes low before phase 2 rises. So they're not just inverted forms of one another. The reason for this is that we want to ensure that certain switches will open before other switches close. And so we don't accidentally start to loop, latch to the wrong data, loop data back to each other, whatever it may be. So in this case, we want phase 1, so the series data switch, to open before we close the feedback loop for phase 2. Otherwise, if phase 1 accidentally is closed when phase 2 closes, we're going to have D coming in and feeding back to Q. We're going to get a violation of our logic. So we close switch phase 1 before we, vice versa, we open switch phase 1 before we close phase 2. And we do this with something called non-overlapping clocks. And non-overlapping clocks are generated still based on the same input clock, but we can generate 2 phases based on that one single input clock. And further on into the slide set, I actually have some interesting circuits, and one of them is a non-overlapping clock generating circuit. And you can look at that at your own time. So that will conclude this module. I will let you flip through again some of the interesting circuits, including the non-overlapping clock generation, ring oscillators, which are commonly used to create poor frequency circuits, as well as look at some what we call built-in self-test. We do that with ring oscillators. And then pulse width generators, which are used for timing, which are used for DC-DC converter or power converter circuits. We use these for a variety of reasons. So we've got a few circuits in there, and I'll let you browse through them yourself. Your book also talks about them. And if you ever need more information or would like to learn more about them, please see me. Thank you.